Hey class, today's part 2 of lesson 4. So this is on the back side of the notes from the last screencast with logs. It's 3.2. So second part, we're going to take a look at this one-to-one property. We're going to look at a lot of properties. I used to line all them out and have you guys memorize them, but what I found was that like these numbers 1 through 6 all deal with those properties. They can all be simplified by just converting from log form to exponential form or vice versa. So I think if we just remember that and get really good at converting between the two, like I showed you in the first screencast, that's going to be better than have you guys memorizing things and potentially make a mistake. So first thing, the one-to-one property. We learned this first box here, it says remember. We learned a couple days ago that with exponents, with an exponential, if you have a to the x equals a to the y, then I know that x has to equal y. So that's if you have one exponential term on the left, one exponential term on the right, same base, then the exponents have to be equal, right? That's the only way that that statement can be true. The same is going to happen when we have a log equation. So you'll see over here, I have if log base a of x equals log base a of y. Notice that this base is the same. If that's the case, then x and y have to be the same. In other words, x has to equal y. Okay, so this won't apply until we get down here to these solve problems. All right, so I'm actually going to jump down there. We'll do a few of these. While we're doing this, let's just note that for all log problems, all logs, the inside of the log, like what you're taking the log of, inside of log, must be greater than or equal to 0. Okay, so if you end up getting a negative number inside the log, then, actually, I'm sorry, must be greater than 0, not greater than or equal to. Come on, Larson. Okay, must be greater than 0. So if you get 0 or a negative number, that would count as an extraneous solution, and you just wouldn't count it. Okay, so log base 9 of y equals log base 9 of 16. I have one log base 9, another log base 9. I know that y and 16 have to be equal to each other. So I set those equal, I solve. Well, that one's already done, right? Y equals 16. Second one here, these are both log base 10. I don't know that that matters a ton, but since it's the same log, right, same base, I can take the inside of each of those logs, and set them equal. So 4 minus 3x has got to equal x plus 2. Adding 3x, I get 4x over here, subtracting 2, and I would get x is equal to 1/2. Okay, next one, natural logs. That's really log base e. So log base e of x squared plus 4 equals log base e of 29. You don't have to switch it. We can still see that it's the same base over here, but I get x squared plus 4 has to equal 29. I'm going to use the square root method, so let's subtract 4 from each side. Oops, one step ahead. Square root, and we get x is equal to plus or minus 5. Okay, let's take a look if any of these are extraneous. I have negative 5, right? Let's plug this back in. So when I plug in 5 squared is 25, plus 4 is 29. That's a positive number, totally fine. When I plug in negative 5 squared, that's positive 25, plus 4 gets me 29. So that's okay too. If I would have gotten a negative number inside here after I plug in x, that's when I would count it as extraneous. So I guess I didn't plug in for number 2. I don't think I needed to really plug in for number 1. When we plug in 1/2 over here, 4 minus 3 over 2, that's going to be positive. 1/2 plus 2, that'll be positive. So no extraneous on any of these. Okay, I'll go through 1 through 6 here. Same approach as the last screencast. By the way, when we set equal to x and then claim that x equals 0, that's the same as the original log equaling 0. So you could write it either way. Remember, if you just have a term with no exponent, it's really 1. Number 3, we're staring at an exponential term. I have a base with an exponent. It just so happens that I have a log in the exponent, but it's still an exponential term we're looking at here. So let's see, log, let's drop the e, swap natural log of 8 and x. Notice that log base e is really natural log, so I have natural log of x equals natural log of 8. Clearly we can see that x is going to equal 8. One-to-one property there. Let's see, convert to log form, same thing. This is an exponential. I convert to log, so log, drop the 8, swap the x and the exponent. Both log of 8. So x will equal 30. 5 and 6 are a little bit different. I'm going to tackle this 15 coefficient separately. Let's do natural log of 1. Let's take natural log of 1, set it equal to my variable. So that's log base e of 1 equals x. E to the x equals 1. I think x, or natural log of 1, would have to equal 0. So this is really 15 times 0, which will get me 0. Next one, I have a log, and then I'm going to divide it by 6. Let's ignore the divided by 6. Let's just focus on natural log of e. Remember, natural log is really log base e. So ln is log base e, and then I also have e inside the log. Set it equal to x, convert it to exponential. So drop and swap. E to the x equals e, that's really e to the first. X is going to equal 1. In other words, log base e of e equals 1, natural log of e equals 1. So this is really just 1 over 6, right? I'm taking that value of the log and dividing it by 6. So that's it. Go ahead on and do some practice, and best of luck to you. Thanks, guys.